Hi everyone, I'm Rahul Rangaraj. I'm from Neural Network, Recurring Neural Network student, and today we are going to learn about the recurrent neural networks and late short-term neural networks. So here uh, I have done a report on LSTM and also recurrent neural networks with some Python codes and also the results of the Python codes. And today we have selected a time series data set, and with the time series data set we have created recurrent neural network models and LSTM. So we'll discuss a brief about LSTM neural networks. So the LSTM is also known as a long short term memory. It is actually the network. It's a recurrent neural network. It is aimed to deal with the vanishing gradient problem, and it the basic uh, the basic relative insensitivity to gap length in the advantages of other recurrent neural networks. So basically, it is most common unit. It is composed of a cell and an input gate, and also the output gate. And also here we have selected Indian climate weather forecasting dataset report, and this particular dataset is have found this from the Kaggle website. The Kaggle website is very helpful for your machine learning and deep learning datasets, and also some other analysis. If you want to do any analysis on anything, any visualization and etc., this particular website will help you a lot. There are many more data sets. Some are cleaned, some are uncleaned, some are revised, and some are unrevised. So I have selected the particular data set of Indian climate, weather climate, from this Kaggle website, and I have provided the download links for the Kaggle website right here. And this is a particular link where I have directly downloaded the dataset from. So this is provided for your reference. So if you want the dataset which I have already dealt with, you can just click on this website and you can go to the Kaggle website, and it is a direct link to the download website. And here, as it is a time series dataset, the dataset consists of the date of start time as January 1st 2013, and the end date is 24th April 2017. So we are going to deal with the data or the information which is between January 1st 2013 to April 24 2017. And most important thing is this is as this is a climatic condition, we have some categorical and variables and also time series variables. So yeah, just to get you remind, and here we can see the it's an overview of the dataset, which includes 1561 days over a period of around 4 years and 4 months. So if you can see, from 2013 to 2017, it's 4 years, and the additional 4 months of the data is included in this particular data set. And here the variables, it is consists of a date, mean temperature, humidity, wind speed, mean measure. So it is explained that in the particular data set, all these variables are included, and we are dealing with this particular term. So date, we can see it as integer, and date format is given, and mean temperature, it is integer, and humidity, it is also if you can, I can show you the data set which I have downloaded. So this is the data set. Here the date is given, and here the mean temperature is given like a 10, 7.4, 7.1, 8.6, and so on. And here humidity is given with the all the integer and decimal type, actually to say. And the wind speed is given like kilometers per hour, like 2.8 4.98 kilometers per hour and 4.633 bar kilometers per hour. And mean pressure is also given as the Pascal unit, 1015.667 pascals, and so on. So here is a overview of a data set which I have chosen, and we go to the report back, and the description of the data sets is given in this way. So it is basically it is telling that the forecasting models tailored to the climate of India, and the data offers a complete collection of daily weather observations for India. Delhi, the main part is we are taking Delhi as the city, the readings of all the data set is took from the city Delhi. And here the modeling climate conditions require the 4 essential parameters. So we have already gone with we are done with the parameters. So these are the essential parameters like mean temperature, humidity, wind speed, and mean pressure. So these are particular 4 parameters which we are gonna concentrate on, because these are we are dealing with so we are comparing and dealing with these particular parameters in the whole data set. And then the report is written in this model. So here the architecture model for a simple recurring neural networks is given in here. So there are 2 layers we are making up with a simple recurrent neural network model. A dense layer with the 1 unit, and a simple neural network layer with 100 units we are taking, and there are around 10,301 trainable parameters in all. So this particular report is we got it from the other thing, and the data on sine waves. So first, the architecture model, we have created a sine waves with the parameters and the values took from the data set. And so here the points are taken as you can see. I'll show you in the Python code where I have actually took the points. So sorry for the inconvenience, let me okay, okay, so here the I took the line space. I took like 0, 30 and 1000 points, as in our data set it is included that it has around 1055 days points is taken, and 30 as a month. I've taken intervals. So with the help of that, okay, let me so again, sorry for the inconvenience, so let me keep it aside. Okay, so here 2 layers make, and the observations are done with it appears like a sine waves underlying patterns, and difficult for the simple neural network model to represent. The model may not be successful learning the sine wave dynamics if the predictions seem to the constant across all the data. So here we can see we have already included all the pandas as PD, NumPy as NP, and a matplotlib library, so that you can visualize the sine wave and all the thing. And we have included also Keras, the TensorFlow. It's machine learning models. So the Keras is used to learn the things. Machine will learn the things. Okay. So here the line space is given like 0 with 30 interval and 1000 points, as we have many like 1000 days, and 30 as the month. Each month the interval is taken, and here we have printed the x and y values, the array, the values from which the data set we have took, it is included in that. And here the plot, we are plotting that with the x and y, the with the help of these two references, we are plotting a sine wave right here. And this is not the thing, but yeah, further we are doing many things. So here the pd.data frame, data is considered as y and index as x. So here the columns and is given as sine. So the sine wave values are given with respect to the x and y values. The sine values are given, and here the length of the df, as we took the length as 1000, so it is printed as 1000. The length will be 1000, and test percent will be 0.2. so the formula for 20% of the thing is taken as length of the df, that is length of the 1000 times the test percent as 0.2. so because we are taking only 20% of the original data set, it is included that 1000 into 0.2. Then we need to find the length of the number of the data set, training data set. So the test length is we taken, and the test length, it's the same length of df into test percentage. We already got like 2000, so we are assigning this particular round cut of to 1000 times 0.2 to the test length. So the test length will be also equal to the 200. So yeah, this is taken in this. It's we are just assigning this particular value, I mean this value, to the variable name called test length. So whenever we want to take the length and times the test percent for 200, we can use this particular variable. Okay, so as we can see, we have chose other variable for integer of length of df minus test length. So the length will be 1000 and the test length will be 200, as we already saw here. So 1000 minus 200, that will be 800, and this particular 800, the value 800 is assigned to this particular variable. So whenever we want the 800, we can use this particular variable and we can deal with that. So here, after assigning all the values, the test length values and also the start index value, we are here to get to create separate training test models. So here the df.ilog is used here for the test start index. Here we already saw test start index value will be 800 and so on. So in this way all the variables are assigned to the values, and here the max scale and the train data set and the normalizing the training data set and length, batch size and normalized train, and the train TS generators are also done in this particular running neural networks model. And these particular tables, you can see the report in the report. I'll explain you later on. And here the y is taken and x dot flatten is taken to get all these x flatten values, and then the epochs are run. Basically the epochs will run, it is such as like it has we have given 5 epochs in this model, and for 5 epochs there are total 750 files to get run. So we have run the 750 in each of the epoch, and for around 5 epochs. Here with the epochs value is given as 5, so here 1 2 3 4 5 times the epoch has run. So it is a actually the epoch is a hyperparameter that defines a number of times the learning algorithm will work. So the particular algorithm we are working on the training data set, so it will learn as many times as we give the number of epochs. So if we have given 5 epochs here, it will again learn the whole algorithm 5 times. what is the data set and how it is trained and how it is gonna deal with the future prediction and so on. So all this you will understand all the thing we have given, and at last the figure is taken in this way, the sine wave is taken in this way. And coming back to the report, so as I already explained you, the sine waves underlying the pattern in the difficult simple RNN, so it is advised to experiment with other designs. So as we have already tried with other designs, so I'll explain you it later on. And so in summary, this particular report offers a preliminary evaluation of a simple recurrent neural network model, and this is like we have trained it in a way that it actually trains itself the whole algorithm. So vanishing gradient problem, so here the vanishing gradient problem is actually explained in a descriptive way, so I'll explain you by learning all the things. Okay, so when an issue arises during the training of deep neural network, especially those with several layers, so if you have many layers in a recurrent neural network, then it will be a problem. Like sometimes the learning algorithm may get stuck, so there's a problem of vanishing gradient. So here the values will disappear when you start learning the same model several times if you have many layers in it. So the here the vanishing there wakes up the vanishing gradient problem, and that is explained here. So it has to do with how gradients or the derivatives of the loss relative to the parameters go backward through the network while gradient descent optimization is taking place. So deep networks can have gradients that are incredibly tiny, almost zero, when they calculate and transmit from the output layers to the input layer during the back propagation, and this could be cause the layers that came before the cease learning efficiently. Since the weights of the subsequent ones receives little changes, it is basically difficult for the user to update the quantities because the knowledge on how to do the decrease together as it goes backward through the levels. In the preceding levels, the network learns meaningful representations. The use of activation functions which with tiny derivatives like the sigmoid or hyperbolic tangent, tan h, you know the angle tan h, that would be sine h by cos h functions, can relatively result in the vanishing gradient issues. Rectified linear unit RELU, the rectified linear unit is abbreviated in the RELU form. Activation of functions including the variations offer a more advantageous flowing gradient for deep networks, allowing them to alleviate this issue. So as we can see, the increasing of the layers may lead to the the input layer during the back propagation, the problem arises. So then we will get to know about the problem of exploding gradient. So right here, the opposite of the optimization of the weights of work receive two large updates when the gradients are and deep architectural networks and recurrent neural networks. So here the during back propagations, gradient get extremely huge rather than overly tiny. The numerical instability and trouble training for the system may result from this. And deep architectural networks and again the RNNs, the neural networks, the recurrent neural networks are more prone to the exploding potential issue. Gradient clipping, which includes scaling gradients if the beyond a certain threshold, is one method for addressing the growing gradient problem. Avoid growing too big and upsetting the training procedure. So here it is explained that many layers, if you are taking the many layers, then you should be aware of overflow of values in a model parameters. So the gradient clipping or the scaling I mean the cutting of the scaling, like the no the value should be not continuous, it should be discrete. The algorithm will learn from the discrete values too, so the discrete values are taken and uh, try to avoid growing too big, so that it could lead to the back propagation, and again the gradient the particular gradient problem, vanishing gradient problem, will also arises in this case. And here the recurrent neural network architecture comes in the form of a simple RNN. Have shown successful in some tasks, but they come with the drawbacks. So we have some limitations right here, and so now I'll explain you that limitations of a simple recurrent neural network. So capturing long-term dependencies is difficult. So whenever the sequential data represents a challenge for a simple neural network to capture long-term dependencies, the associations, learning associations, spanning many times steps, it will take it will run many times, that steps are taken many times in the early inputs, have a decline amount of an impact. So this is one of the drawback we have in a simple RNN. And issue with the vanishing gradient, I already explained you about the vanishing gradient. It will be a huge problem, so we have to take care of giving too much learning algorithm to the model. And also the problem of exploding gradient, it is also explained in the above section, like it should not taken the like many and large there is a problem of back propagation in this, and restricted ability to store sequential data. So simple RNNs can only store a certain amount of data from previous time steps. It constrains, like it's also one of the limitation, like a natural language problem processing jobs where dependencies that last forever and are essential. And also the one of the limitations is unable to manage different sequence lengths. So the model cannot handle different sequence lengths. So the sequence lengths are taken by, it can be it is difficult to handle variable length sequences, and in the real world applications it is frequently needed. So the techniques and also the masking may needed to get rid of that limitation. And after that, learning complex patterns can be difficult. So in particular, where connections where with simple RNNs may find it difficult to understand complex patterns in data. So tasks requiring a greater degree of abstraction make the limitation more noticeable. And the other limitation comes like prone to problems with the gradient descent. So here the difficulty is caused by disappearing and bursting gradients. So again it is kind of related to the vanishing gradient issue. So yeah, this is the thing. And high computation cost. So as you know how as the layer increases, the cost is also increased. So we should avoid cost cutting too. So yeah, and here it is compared with the gating system and also the vanishing gradient in this particular section. So if you can see, shortcomings are the long-term memory LSTM networks in order to better capture long-term dependencies in sequential data. So here the cell state of memory cells are took, like LSTM solve the vanishing gradient issue by introducing a memory cell and a cell state, retaining crucial information across extending sequence is made possible by the cell state. And also the gating systems. LSTMs have like gating systems, as we already discussed in the earlier of this video, an output gate, an input gate, and forget gate. So yeah, here there is we can reduce it by allowing network to reject less pertinent data, and the forget gate helps to avoid the increasing gradient issue. And then all these you can see in the report, like ability to acquire extended during dependencies. It is like resolving the shortcoming of the simple neural networks, and also managing sequences of changing lengths. This is also one kind of limitation which we can which we can see in this particular thing. And here, effective memory management, the workaround for simple RNNs shortcoming in the particular thing, and then can increase its efficiency and identify pertinent patterns. And here these are the limitations that we discussed till now. And so yeah, and then the next section would be the LSTM model. I have run few lines of Python code for LSTM2. I wish I could explain you. Yeah, so these are the LSTM models I have already run in the Jupyter notebook. So here we have included the path of my downloaded thing, like a daily climate train. This is a data set I have already told you that I have downloaded from the Kaggle website, and I have included the link in the video, in this report. Okay, so here the head values are also given in this, and here the all types are taken in this, all the measurements and also the variables are taken here. And here you can see this will be the output of the figure, the plot of this particular data set for long short term model. And here the all the things are given. And for this part, the whole Python code, I have written a report mentioning all the values and all the variables in that. So here the overview of the data set is given. An LSTM model descriptive report, yeah, it is a report we have included in the part 4. So here the model architecture, so we have already discussed the limitations. So to avoid model overfitting, the LSTM model is constructed of 3 LSTM layers. We have included 3 LSTM layers in this particular model, and which is followed by a dropout layer. A dense layer with one prediction unit makes up the last layer, and there are total 50,851 parameters in the overall model. So each variable have the whole values are taken, and there are around 50,851 as per the report we got from the Python coding. And the model performance, training metrics, validation metrics, and the comparison of actual and projected values visually aid in evaluating the model performance. So this you should make a note of. And the observations are done in the LSTM model to capture temporal relationships in the meteorological data. So here the observations and suggestions are also mentioned, as we have learned about many limitations. So to avoid that limitations and to get very accurate and a good value of a good result, you can take the suggestions from here. And the conclusion and the model architecture and statistics of the data set is also included in this particular report. So whenever you get this report, I'll include the report in the in the description. You can check out the reports in this. And the model construction and training model is also given in this. So just go through the whole report and just look at the description, and like also the Python codes I have included in this model. So you go through all of this and you will get to know what the recurrent neural network, and also you will get to know how the layers should be chosen depending on the data set, how many layers it should choose, and how many the epochs, the learning steps, the learning cycles is done by the model to get very well know about the data set. So yeah, that's the thing. And I hope you like this video, and please go through all the stuff and practice the recurrent neural network, simple and recurrent neural network, and long short term model too. All right, see you again.